All right. We are going to look at day one of section 6.7 and 6.8. We're going to be looking at polygons in the coordinate plane, and we're going to start building towards this concept that's called a coordinate proof. It's not a two-column proof, so we're not going to be making a statement and reasons chart, but it is more of I would say, an algebraic type of proof. What we're going to be doing, the ultimate goal of this section is we're going to be given ordered pairs, and we're going to plot them on a coordinate plane, and we're going to decide, once we connect the dots, what is the most precise name for the quadrilateral that we've graphed, without just eyeballing it and saying, it looks like a rhombus or it looks like a rectangle. We want to use the properties from our quadrilateral family tree that we've been constructing this entire unit in order to decide with mathematical accuracy based on the properties what shape is that. Okay, not this particular one, but so before we do that, we need to do some review of three formulas that are going to help us quite a bit with this section. And that's the slope formula, the midpoint formula, and the distance formula. So we're going to review those first. And I said the ultimate goal is to be able to plot a quadrilateral and use mathematical evidence to give a precise name for the figure that we plot. Okay, just a quick recap of our formulas, and then we'll get into the heart of this section. Your slope formula, remember slope on a graph, you could calculate it as rise over run. It's the change in y over the change in x. If you're going to use the actual slope formula, slope is m. That's y2 minus y1 divided by x2 minus x1. And I'll point out to you how we would use this on the coordinate plane in a little bit. The midpoint formula, if I had a segment with two endpoints and I wanted to know what point divided that segment into two congruent segments, my midpoint formula, it's an ordered pair. We do x1 plus x2, and we cut that sum in half. And then we do y1 plus y2, and we cut that sum in half. The distance formula tells me how long a segment is, if I wanted to know the length of a segment. And this is all, by the way, for two ordered pairs, x1, y1, and x2, y2, every single one of these. So if I wanted to know the distance between those two ordered pairs, the distance between them would be the square root of x2 minus x1 all squared plus y2 minus y1 all squared. Okay, so let's take a look and just recap how to use these with numbers. Let's say I have 2 points, 0.31 and 2.5. I'm going to let this be x1, y1. I'm going to let this be x2, y2. And I want to answer the following questions. Number one, I want to find the midpoint of segment AB. So I'm going to use my midpoint formula in the middle here. Midpoint, I'll call it M, is going to be x1 plus x2 divided by 2. So substituting in my numbers from here, I would get 3 plus 2, cut that in half. y1 plus y2, 1 plus 5, cut that in half, and then simplify my answers. This would be 5 halves, which doesn't simplify, and 1 plus 5 would be 6 halves. So I can reduce this to 3. So 5 halves, 3. You could also call this one 2.5 if you want. Okay, find the length of AB. So length, if I see length, that means I'm talking about distance. So I would want to use my distance formula. Notationally, remember the way that we would denote this is AB without the overbar. I'm not naming the segment. If I don't put the overbar, that means I'm taking the length of the segment. So this would be the square root of x2 minus x1 squared. So 2 minus 1 squared. I'm sorry, 2 minus 3 squared, not 2 minus 1 squared, plus y2 minus y1 squared, 5 minus 1 squared. And then I'm going to, remember, I'm not going to take the square root until I'm all done. So I'm going to get negative 1 squared plus 4 squared. And you could put this in your calculator, but I'm going to do it one step at a time. Negative 1 squared, remember, would be positive 1. 4 squared would be 16. I'm going to add the two numbers, 17, and then put a radical over it. So my distance would be rad 17. And you could get the decimal version of that. I'm just going to give you a heads up. For the purpose of this section, we're going to leave them, unless they come out to nice clean square roots like square root of 25 or square root of 16. We're just going to leave them in radical form because that's all we need, is we're going to need them to match when we do the problems in this section. Last one, we need the slope of AB, so the rise over run, the steepness of that line. This would be y2 minus y1 over x2 minus x1. And my ordered pairs ran out of space, so I'm going to rewrite them over here. A was 3, 1, and B was 2, 5. This was my x1, y1, and this was my x2, y2. So my slope would be, ooh, there we go. I think I'm still there. Okay. Y2 is 5 minus y1 is 1. X2 is 2 minus x1 is 3. And then I'm going to simplify the numerator, I get 4, and I'm going to simplify the denominator, I get negative 1. 4 divided by negative 1 would be negative 4. Okay. Couple other reminders. What do we know about lines with equal slopes? Those lines would be parallel. Parallel lines have the same slope. Remember, if lines have opposite reciprocal slopes, or if the product of their slopes is negative 1, those lines would be perpendicular. And I'm going to remind you of the symbols. Parallel looks like that. Perpendicular looks like that. All right, so what we're going to start, and let's start with triangles before we get to quadrilaterals. One type of question you could see is to ask you, if they give you the vertices of a triangle, or if they give you the picture of a triangle on the coordinate plane with 3 given vertices, how do you decide if the triangle is scalene, isosceles, or equilateral using coordinate geometry? So reminder, if a triangle is scalene, that means no sides are congruent. No sides have the same length. Isosceles means 2 sides are congruent. 2 sides have the same length. And equilateral means all 3 sides are congruent. All 3 sides have the same length. Notice what I said for each one of these. Length. Side length. Which formula deals with length? Put your prediction down, pause me, and then you can check it. You would want to use the distance formula. So what I'm going to do, they gave me 3 vertices of this triangle. This vertex A is at 0, 1. This vertex B is at 4, 4. And this vertex C is at 7, 0. I'm going to want to calculate 3 different lengths. I'm going to want the length of AB. I'm going to want the length of BC. And I'm going to want the length of AC. And I'm going to compare the distances of those sides that I get. If all 3 of those lengths end up being equal, then the triangle will be equilateral. If only 2 of those sides end up having the same length, the triangle will be isosceles. And if none of the values of those lengths are equal, then the triangle is going to be scalene. So unfortunately, I am going to have to use the distance formula 3 times. So AB, I'm going to first focus on this segment here. I'll do this one in red. This is going to be the square root of x2 minus x1 squared would be 4 minus 0 squared, plus y2 minus y1 squared would be 4 minus 1 squared. And then I'm going to simplify. 4 minus 0 squared would be 4 squared. 4 minus 1 squared would be 3 squared. This gives me the square root of 16 plus 9, which is the square root of 25. The square root of 25 is 5. And by all means, you can use a calculator if you need to check any of those. I can't narrow out down anything yet because I've only calculated one side. I'm going to need to look at least one more side before I can rule out one of these 3 vocab words. So I'm going to calculate the length of BC. Let me maybe do a different color so that you can focus on this one now. I'll do green for this one. So now I'm looking at 4, 4 and 7, 0 as my 2 ordered pairs. Okay, so here's my x1, here's my y1, here's my x2, here's my y2. I'm going to do distance formula again. X2 minus x1 squared would be 7 minus 4 squared, plus y2 minus y1 squared would be 0 minus 4 squared. So I get the square root of 3 squared plus negative 4 squared, and I get the square root of 9, still plus 16. Anytime we square a number, we get a positive. And I still get the square root of 25, which is 5. So at least at this point, I know it's not scalene because I already got 2 sides congruent. So it's at least isosceles. Now I need to check that 3rd side to see if it's equilateral. So I'll do this one in blue. I'm going to calculate AC. Last one. So now this will be one ordered pair I'm using. This will be the other. Let's now make this our x1, y1. Let's make this our x2, y2. Last time, I promise for this problem, it's the last time we have to use the distance formula. It's not our favorite, I know. X2 minus x1 squared will be 0 minus 7 squared. plus y2 minus y1 squared will be 1 minus 0 squared. And so I get negative 7 squared plus 1 squared gives me 49 plus 1. Okay, square root of 50 is definitely not the same as the square root of 25. So this is definitely not equal to 5. So these two are a match. This one is not. Two sides have the same length. I'm actually going to mark them in the picture. I'll use black. This side and this side had the same length and this side did not. So it's not equilateral. So I would write my conclusion, triangle ABC is isosceles because only two sides are congruent. And those two sides are AB and BC. Okay. And I backed it up with calculations. And this is an example of what's called the coordinate proof, is we're using calculations to support our claim that we make at the bottom. I'm still using some words, you'll notice, right? I'm still explaining my answer at the bottom, but I'm backing it up with calculations. So this is a good one to kind of get us started. All right, let's up the number of sides. Let's now move on to some quadrilaterals. And we're not going to do a full-out coordinate proof right now. I just want you to kind of start to think about what formulas you would have to use to check certain properties that we've talked about. So some of the different properties we've talked about are both pairs of opposite sides are parallel. And you have to think, okay, now we're on the coordinate plane. How do we check if lines are parallel on the coordinate plane? Well, we check that they have the same slope. Okay, so, you can see where some of these calculations might start coming into play now. What if I wanted to check if diagonals are congruent? Well, if I want to check if diagonals are congruent, that would mean they have the same length. So I would have to use the distance formula. And I could continue this list. I don't want to make this too long, so I'll kind of do it throughout the problems. But just to give you an idea, all the properties we've talked about in the quad chart can be applied on the coordinate plane with a little bit of justification. It's either going to be midpoint, distance, or slope, and I'll kind of give you some tips as we go. So here I've graphed for you quadrilateral tune, T-U-N-E. Maybe put the vertices in red. T-U. Hey, it's a tune. I should sing it. T-U-N-E. Okay. There's the math song of the day. First thing in part A, these are all separate problems. I want to show that TE is parallel to UN. I'm going to highlight those in red. And I want to show that EN is parallel to TU. So I'll do those in blue. Okay, so anytime I see parallel, if I'm on the coordinate plane, parallel tells me what formula am I going to need? Slope. So I know I'm going to do, now I'm going to put the formula up, but then I'm going to tell you on the graph, I always think it's just a lot easier to count when it's slope. I would just do rise over run. Okay, midpoint or distance, I would say stick to the formula, but rise and run is very easy to count as long as you remember your friend Mr. Slope Guy. You got to remember if these slopes are positive, negative, 0, or undefined. So we'll look at those as we go. So the first one I'm going to need to calculate is the slope of TE. So I'm going to label that slope M, and as a little subscript, I'm going to write the segment TE. And the way I would read that is the slope of segment TE. And if I look at it, the TE has a positive slope. It's rising to the right, and it goes up 1, 2, 3 over 1, 2, 3, 4, 5, 6. So my slope would be 3 over 6, which reduces to 1/2. And then I'm going to take the slope of UN. If it's truly parallel, then it should also come out to 1/2. If I look at this one goes down 1, 2, 3, and goes over 1, 2, 3, 4, 5, 6. So this would also be a positive 3 over 6 slope. And so what I've just shown right here is that the slopes are equal. So TE is parallel to UN. Notice that I'm kind of writing the geometry that follows from that algebra that I just checked. And now I'm going to check this one in blue. So I did this one in red. I'm going to highlight. That one was red. Now I'm going to do this one in blue. I want to check that the other set of sides is parallel. So I already proved this one. I'm going to mark arrows on my shape. Those are parallel. Now I'm running out of space. Let's go. Oh boy, where should I go? I can fit it. I'm going to go over here. Slope of, let's do EN first. So now I'm looking at this segment right here. This one goes down 1, 2, 3, 4, 5, 6, 7, 8, 9. Nope. It goes down 1, 2, 3, 4, 5, 6, 7, 8. Oop. Over 1, 2, 3, 4. And it's a negative slope because it's falling to the right. So this would be down 8 over 4 would be negative 8 over 4, which is negative 2. And then I'm going to do the slope of TU on the other side. This one goes up 1, 2, 3, 4, 5, 6, 7, 8 over 1, 2, 3, 4. So this also has a slope of negative 8 over 4, which is negative 2. And so these two are equal. That tells me EN is parallel to TU. Okay, so we have shown that TE is parallel to UN by showing those two have the same slope of 1/2. And we have shown that EN is parallel to TU since those both had a slope of negative 2. I'm going to put double-sided arrows. So at this point, what have I shown? I've actually shown that this is a parallelogram because I've shown that both pairs of opposite sides are parallel. So just kind of, off to the side, I'd be thinking to myself, okay, I know that this is at least a parallelogram. And by the end of the problem, what I'm trying to get you to work towards is thinking about what's the most precise name for this shape. And in this first problem, I'm kind of guiding you through it with the different kind of parts that we would be checking along the way. Eventually, you're going to write these from scratch without the hints, but I want to kind of guide it first. So now underneath, we know there's still rectangle, there's still rhombus, and there's still square that it could potentially be. So we're probably going to have to check some other properties before we can answer those questions. Another way I could have shown it's a parallelogram is I could have shown that the diagonals bisect each other. So let me kind of show you an approach for that one. If I wanted to prove that the diagonals of two bisect each other, remember that means they split each other in half. So if I was sketching this out of the coordinate plane, that would mean these two pieces are congruent. And that would also mean these two pieces are congruent. And what that tells me is that this point in the middle is a midpoint of both of those diagonals. Both of those diagonals have the same midpoint. So if I want to show on the coordinate plane that diagonals bisect each other, I'm going to need to use the midpoint formula. x1 plus x2 divided by 2, y1 plus y2 divided by 2. And I want to show that they have the same midpoint. Okay, so I'm just going to calculate it twice. One of my diagonals is EU. So I'm first going to find the midpoint of EU. And so I'm going to highlight this in green. Here's EU. E, what are the coordinates of E? Let's see. E is at negative 6, 7. I'm just going to write these down so I have them. And U is at, looks to be at 4, 2. So I'm going to find the midpoint. Here's my x1, y1, x2, y2. So my midpoint is going to be negative 7 plus 4 divided by 2, 7 plus 2 divided by 2. I get negative 2 over 2, which is negative 1, and I get 9 over 2. So now I want to check the other one. I'll do this one in green also. Here's my other diagonal, TN. Looks like T has coordinates at 0, 10. And it looks like N has coordinates at negative 2, negative 1. So here's my x1, here's my y1, here's my x2, here's my y2. I want to find the midpoint of Tn. And so I'm going to use the same formula, and I'm hoping it comes out to negative 1 9/2. That's my goal. So I'm going to do 0 plus negative 2, 0 minus 2 divided by 2, and 10 plus negative 1, 10 minus 1 divided by 2. And I get negative 2 over 2 is negative 1. 10 minus 1 is 9 over 2. And if you compare, they have the same midpoint. These are equal. So the diagonals do bisect each other because these are the same midpoint. So now I know, which I already guess I could have figured out, right? Because I already said it was a parallelogram, so that shouldn't be too surprising. Part A and Part B are just two different ways of going about showing this as a parallelogram. Personally, I always stick with Part A as my go-to to prove it's a parallelogram. I just think that counting rise over run is very simple to do instead of having to use a formula. Show that the diagonals of two are congruent. Okay, if the diagonals are congruent, that means they have the same length. Diagonals congruent means same length. And which formula has to do with length? The distance formula. x2 minus x1 squared plus y2 minus y1 squared. And so what I'm going to have to calculate, the order was what? T, U, N, E. I kind of rotated it over here, but you get the idea. So I'm going to have to show, my goal is going to be to show that the length of EU is equal to the length of TN. Okay? And I've already got the coordinates here and here, so I'm just going to use those. So EU would be the square root of x2 minus x1 squared would be 4 minus negative 6 squared plus 2 minus 7 squared. And so I end up with the square root of 4 plus 6 would be 10 squared, plus 2 minus 7 would be negative 5 squared. This would be 100 plus 25, so this would be the square root of 125. And I'm just going to leave that. I don't care about breaking down the radical right now. I don't care about getting a decimal. That's not the point of this. The point of this is to show that you get a match. Whether that match is a messy decimal or not, it's a match. Tn, so now I'm going to use these two ordered pairs. I want to find the length of that diagonal. That's going to be the square root of x2 minus x1 squared would be, I'll let this be my x1, y1, and the order you do x1, y1, and x2, y2 doesn't matter. As long as x goes first and y goes second, and as long as you keep the ones in one ordered pair and the twos in the other ordered pair. So this would be negative 2 minus 0 squared, and this would be negative 1 minus 10 squared. So I get the square root of negative 2 squared plus the square root of negative 11 squared. And so I get the square root of 4 plus a negative 11 squared is 121. And so I get 125. And yes, we do get a match. These are equal, so that tells me that the diagonals are congruent. So now what do I know? In part B, I showed they bisected each other. Now I know they're congruent. So now if we go back to our little chart that I drew, we knew it was a p-gram. Think to yourself, which one do we know it is now? And you should be thinking, okay, now I know it's at least a rectangle. How do I now further decide if it's a square? Well, I need at least one rhombus property, and that's what the point of the next part is. In order to check if it's a rhombus, so this basically told us at this point, now we know it's a rectangle. So now I'm going to go to D. In order to show it's a rhombus, I need to check to see if I could check a couple things. I could check if the shape is equilateral, but then I would have to use distance formula again to find the side lengths, and I don't think we want to have to use distance formula again, right? Another way of showing it's a rhombus is to show that the diagonals are perpendicular. If the diagonals are perpendicular, it's a rhombus. And we know how to check for perpendicular. Perpendicular would mean that the slopes are opposite reciprocals. And notice in this problem, it's kind of telling us going into it, we want to show that these diagonals are not perpendicular. So we're trying to show right now that this is not a rhombus. And the way we're going to do that is we're going to show that the slopes are not opposite reciprocals. Not opposite reciprocal slopes. So we're going to need to use rise over run to prove that. So calculations, I'm going to find the slope of my two diagonals here in green. So I'm going to want the slope of Tn, and I'm going to want the slope of EU. You could use the slope formula, or you could count. I'm just going to count. So I'm going to go up. Let's see. 1, 2, 3. I'm going to go from N to T first. And it's a positive slope. I can see that because it's rising to the right. It's going to go up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 over 2. So this one has a slope of 11 halves. I'm going to double check that one more time because it's easy to miscount. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 over 2. Okay. EU has a negative slope. I can see that. And it goes, I'll go from U to E. I'm going to go here to here. It goes up 1, 2, 3, 4, 5 over, let me try that again. 1, 2, 3, 4, 5 over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. negative 5 over 10, which is negative 1/2. Negative 1/2 and 11 halves are not opposite reciprocals of each other, right? There we go. So slope of, I'm just going to copy what I had at the top. Slope of Tn was 11 halves. Ooh, too much. There we go. Slope of Tn is 11 halves. Slope of, what was the other one? EU is negative 1/2. And so these are not opposite reciprocals, slopes. Therefore, the diagonals are not perpendicular. So this is not a rhombus. That's what we've just ruled out. The diagonals don't intersect at 90 degrees. So here's my logic now. Let's kind of summarize what we've done. By showing in part A or in part B, in part A, we did that the opposite sides were parallel. That gave us that it was a parallelogram. In part B, we confirmed that. We showed that the diagonals bisected each other. Going down the chart, so what have I ruled out now? What I've ruled out is that this was not a trapezoid and this was not a kite. I know that I'm focused on just the middle part here. Then the next thing I noticed, we calculated the diagonals and showed that they were congruent. Both of them had a length of rad 125. So that told me it's a rectangle. And then last but not least, what I checked was that in order to check if it's a square, I have to check. I checked a rhombus property. I checked to see if the diagonals were perpendicular, and we showed that the slopes of those diagonals were not opposite reciprocals. That means that those lines, those diagonals, could not be perpendicular, so it was not a rhombus. And if it's not a rhombus, then it can't be a square. So the most descriptive name for this shape would be a rectangle. And that's what we're working towards, is being able to construct this argument on our own. The point of this example is for you to see the logic that goes into using those formulas to draw that conclusion. So let's try another one. We've got here quadrilateral A, B, C, D, and it's been drawn already. Today I'm going to draw them for you. And I want to, this one's making it kind of clear. It wants me to show that it's a trapezoid. Eventually, it's not going to tell you which one it is. You're going to have to decide. But right now, I'm going to kind of make this one a little simpler. I'm telling you going into it, it's a trapezoid. So what are you going to have to show? You have to know your definitions from your family tree in order to do these problems. Even though there's algebra involved, you still got to know the properties so that you know what to check. So think maybe, try to quiz yourself on your properties. What's the definition of a trapezoid? If you need to look, go ahead and take a look. The definition of a trapezoid is we have one set of parallel sides. Those are the bases. And one set of non-parallel sides. Those are the legs. And so what I'm going to have to show is I'm going to have to show that one pair of sides is parallel, but I'm going to have to also verify that the other set of sides is not parallel. I can't just assume that. I have to show that. Looking at the picture, I can kind of get an idea for which ones appear to be parallel. So my goal is going to be to show AD is parallel to BC. And therefore, step 2, I'm going to have to show the other ones, AB and CD. Those do not look parallel. I'm going to show that AB is not parallel to CD. And how am I going to do this? Anytime it mentions parallel, I'm going to use slope. So I'm going to do rise over run for each of those line segments and compare. I'm going to start with the ones that I am trying to prove parallel. I'm going to start with the red ones. So I'm going to find the slope of AD and compare it to the slope of BC. Slope of AD is, both of them are negative slopes. Here's Mr. Slope Guy. I can see both of the lines are falling to the right. From A to D, it goes down 1, 2, 3, 4, 5, 6, 7, 8 over 1, 2, 3, 4. Down 8 over 4, negative, gives me a slope of negative 2. And then I'm going to do the slope of BC. Slope of BC, I'm going to go from C to B this time, goes up 1, 2, 3, 4, 5, 6 over 1, 2, 3. Negative 6 over 3 would be negative 2. Same slope. If lines have the same slope, geometrically, that means that those two lines are parallel. And I need to mention that. This is something you have to write. You can't leave that up to the reader to infer. You have to make that claim. So we've shown step 1. Now we move on to step 2. So I'm going to actually label my steps. This was step 1. I'm going to stay organized. Now I'm going to do step 2. I'm going to show in blue that the other 2 lines or the other 2 segments are not parallel. And I'm actually going to mark the ones I just found parallel with an arrow. So now I know those are my bases. Let's try to show that the other ones aren't congruent, or are not parallel. So I'm going to have to show if parallel means same slope, then not parallel would mean not the same slope. I'm going to have to show that they have different slopes. So the slope of AB is equal to, this time it's positive slope for both of these. It's going to go up 1, 2, let's see, up 1, 2 over 1, 2, 3, 4. 2/4 would be a half. And the slope of DC or CD would be, this goes down 1, 2, 3, 4 over 1, 2, 3. So we're going down down 4 over 3. So this would be a slope of positive 4/3. And clearly, 4/3 and 1/2, these are not equal. So what that tells me is that those slopes are not equal. So those lines A, B, and CD are not parallel. And so therefore, we have shown this as a trapezoid because we've shown that one pair of sides is parallel and one pair of sides is not parallel. So therefore, we know ABCD is a trapezoid. And we've confirmed that, and we've made notes of that along the way. So that's good enough for that part. Okay, so this is a proof, right? It's not a 2-column proof, but it's called a coordinate proof. We're proving using these formulas on the coordinate plane the properties that we've been talking about the whole chapter. Now a follow-up question. I want to know if the trapezoid is isosceles. What do we need to show? There's many different routes we could take. You have to think about your properties of isosceles trapezoids. The ones that deal with base angles are very hard to do on the coordinate plane because we don't have a way to measure angles with the formulas that we've talked about, unless we're looking at perpendicular, but there is no perpendicular properties for trapezoids. So we're going to have to stick to ones that deal with length. So I would either need to show one of our properties was the legs are congruent. That's one route I could go. Or you could show the diagonals are congruent. You don't need to do both of these, but you have to kind of pick one and proceed with one of them. You already know it's a trapezoid. You've already established that. So if you can show the legs are congruent, you've done your job and proven it isosceles. Or if you prove the diagonals congruent, you've done your job and you've proven it isosceles. Anytime we're trying to prove lengths are congruent or lengths are equal, segments are congruent, it has nothing to do with parallel or bisecting. You're going to have to use the distance formula. Unfortunately, there's no way around it. I would suggest, here was our leg, here was our leg. Instead of having to draw diagonals and draw more segments, why don't we just use the distance formula on the 2 legs that we already have in the picture? So what are we going to have to show? Instead of sketching diagonals, I'm just going to show the legs AB and CD are congruent. So my goal is going to be to show that the length of AB is equal to the length of CD. Okay. And I'm going to list the ordered pairs so that I can have them right here. So A, just so I have them, A is negative 3, 3. B is 1, 5. C is 4, negative 1. And D is 1, negative 5. Okay. And so we're going to use the legs were A, B, and CD. So I'm going to focus on these 2 first. I'll do these in red. I'm going to calculate the distance from A to B, the length of AB. So I'm going to have x2 minus x1 squared. So x1, y1, x2, y2. 1 minus negative 3 squared plus y2 minus y1 squared. 5 minus 3 squared would be, this would be 1 plus 4 squared plus 5 minus 3 squared. I'm going to keep going. This gives me 5 squared plus 2 squared. So I get 25 plus 4, which is rad 29. And now I'm going to do the other one. I'm going to do CD. I'll do this one in blue. I'm going to make this x1, y1, x2, y2, big square root, x2 minus x1 squared, 1 minus 4 squared, plus y2 minus y1 squared. Move myself out of the way there. -5 minus -1 squared gives me -3 squared plus -5. This would be +1. -4 squared. This gives me 9 plus 16, which is rad 25. Honestly, at this point, you could stop. I'm going to just take it one step further because I know what that is. Clearly, these are not equal, right? Those lengths are not the same length. I'm even going to mark that on here. This one has length rad 29, and this one has length rad 25. There we go. -3. I'm just double checking my calculations here. Oh, you know what? Oh, yeah, no, okay, we're good. No, you know what? Actually, pause. Nope. I got to go back and fix this one here because this 1 minus -3 is 4 squared. Hang on. Sorry about that. This part right here should be 1 plus 3 squared, not 1 plus 4 squared, right? So this would be 4 squared plus 2 squared. There we go. So this would be 16 plus 4. Sorry about that. Regardless, we get the exact same solution, right? Rad 20 and rad 25 are not the same length. The first one we did is shorter, and the second one we did is longer. They're not the same length. So what that tells me right here, this tells me right now that, what's my conclusion from this? My conclusion from this is that the length of AB does not equal the length of CD. So I know AB is not congruent to CD. In other words, my legs are not congruent. Therefore, final conclusion, this is not an isosceles trapezoid. It would be a trapezoid because we showed that in the first part, but it would not be an isosceles trapezoid because the legs are not congruent. So A, B, C, D is not an isosceles trapezoid. Okay. All right, the rest of this handout you do not need to fill out right now. We will pick up with this on Monday for now, or when I see you next. If you're watching it in this school year, it's going to be Monday. If it's a different school year, it might be a different day. But your homework is to work on the 6, 7, 6, 8 day 1 math Excel. So have that done coming to class for Monday so that we can pick up with this one on Monday. We're going to show this as a kite as our warm up, and then we're going to start doing some coordinate proofs from scratch. We're going to plot the vertices ourselves, and we're going to plan out what we want to do in order to show what the most precise name for the quadrilateral is using the techniques that we just talked about. Okay, until next time, happy mathing.